Okay, so when you look at the key terms that are involved in kinematics in what will be a higher level or standard level syllabus will be basically uh, displacement, velocity, acceleration, and speed. So obviously velocity and speed more looks familiar to us. Now displacement, acceleration, we as a physics student, in case if we know already, good, but displacement is basically when you talk about the um, uh, let's say the motion problems. Displacement is the initial to final position if you join, or whatever is the net distance between these 2 points, that's called as the displacement. Now if you went via 10 different paths, but you eventually came to, let's say, B, your displacement from initial to this position is going to be just a straight line segment joining this, while your distance will be the sum of the paths that you took to come to this point. So let's say you came by this path, and so you're going to add up all the lengths, and that will be your distance. So distance, as you know, is a scalar quantity. It's a scalar number and doesn't require basically direction to be expressed, while displacement needs to be defined in terms of direction. So displacement is a vector quantity. Uh, Coming back to the velocity, now velocity as we define is that at what rate your displacement is changing. So at what rate you're moving. And so since it is engaging the displacement, that's where your velocity is defined as a vector quantity. So displacement is velocity definition is basically rate of change of displacement. Now acceleration, when you define, is at what rate your velocity is changing. So you can say that acceleration is rate of change of velocity. So rate of change of velocity. Uh, so if velocity changing at increasing at regular time interval, then acceleration is like also increasing. If velocity is slowing down and eventually comes to, let's say, constant value, then acceleration also becomes like, slows down, reduces, and comes back to the, let's say, zero. So if there is no change in velocity, the acceleration is zero. So speed, when you talk, is just the distance, at what rate the distance is changing, and it's a scalar quantity. So distance upon time is basically the speed. Now we'll be talking more explicitly when you're talking about the derivative. We'll be talking more explicitly about these three key terms. So let's just explore the major key concept hidden in these. So there are certain rules that we need to apply in order to understand this topic better. So kinematics, if you just look at the general like definition, we have that rate of change of velocity is acceleration, rate of change of displacement is velocity. But first understand when these quantity like displacement is positive, when displacement is negative, when displacement is zero. So actually we consider like x-axis as like a main reference line. And if, let's say, a body is towards the right side of the origin, let's say if I'm standing here at this point, then I'm, let's say, 5 meters away from the origin, my displacement will be positive 5. But if I'm standing 5 meters to the left of the origin, my displacement will be negative 5. So when you are when you're standing to the right side of the origin, the displacement is positive. If you're to the left side of the origin, displacement is taken as negative. And of course, if you're sitting at the origin, your displacement is zero. So when you'll be doing mathematical problems, you will have to talk about the origin as the reference frame, that from origin, this is the displacement. From origin to the left or right of the origin. So these key terms will be very, very important when you will talk about the displacement. So when you talk about the velocity now when you say that instantaneous velocity, obviously there is a like average change in velocity that we're not talking about. When you talk about instantaneous velocity derivative, you know that it gives you the slope at that point. So when you talk about the derivative, so suppose let's say derivative of displacement function. So when you say this derivative of displacement function will be ds upon dt, that will be referred as velocity, because the rate of change of displacement is velocity. So ds by dt is referred as velocity. Now coming to this, it's sign notation. Like when I draw the sign diagram for velocity, what does the velocity being positive mean? Velocity being negative mean? Now, when velocity is positive, the object is simply moving towards the right. When velocity is negative, the object is moving to the left. Once again, here the reference frame is the x-axis. If the velocity is positive, it is moving in the right sense. If velocity is negative, it is moving leftwards. And if velocity is zero, that at that point the particle is at instantaneously at rest. So this is the sign convention of the velocity. Let's take the sign convention for the acceleration finally. So when you talk about the acceleration, now since you know the acceleration is rate of change of velocity, so either you can say acceleration is derivative of velocity. So if you have velocity expression and you differentiate that, you get straight away the acceleration. Or if you have the displacement equation, you differentiate it twice. So if I have, let's say, displacement equation as, let's say, s of t is, for example, t 3t cubed plus 5t squared, my velocity function will be v of t will be derivative of this, which is 9t squared plus 10t, and the derivative of this will be acceleration function, which is 18t plus 10. So this is the acceleration expression. Now, when you define acceleration, now it's really important to understand the links, the minutest link. Like for example, when acceleration is positive, when acceleration sign diagram is negative, um, I mean, how does it impact the entire motion? So we'll take one proper example in order to understand the key concepts linked up with the velocity, acceleration, and the displacement. So let's take one proper example to understand all the key concepts. So as a general trend, what you can remember is that if you want to go from displacement to velocity, you differentiate that displacement equation. If you want to go from velocity to acceleration, you differentiate that expression one more time. And if you go on to go from acceleration to velocity, you obviously integrate that expression because you're just doing the opposite of what you did for derivative here. And if you have the velocity expression and you want to find the displacement equation, you integrate once again. So this is the general link between the derivative and integration for the kinematics. And now let's just take the example which can clarify our key concepts. So first thing is that a particle moves in a straight line with position relative to the origin is given by s of t's t cubed minus 60 square plus 90 minus 1 centimeter, where t is greater than 0. Question is that find out expression for particles velocity, accelerations, and sign diagram for, and draw the sign diagram for each of them. Now, so when you draw the sign diagram or find out the expression, you need to be very careful and be informed about the key concepts of the sign diagram, because one thing goes wrong and rest of your analysis will go wrong. So just be sure of how to draw sign diagram. So now question here will be that v of t expression is going to be 3t squared minus 6t plus 9. So 3t squared minus 60 plus 9 is v of t, and acceleration sign diagram will be 6t minus 6. So when you want to find out the sign diagram,
So
for
it will
each,
be 12t.
yes, thanks. This will be 12t. Okay, all right. So the first derivative will be the derivative displacement will be 3t squared minus 12t here plus 9, and the derivative of the acceleration time expression is going to be 6t minus 12. So this is the basic expression for each of them. And now to draw sign diagram, you all know that you need to equate this to 0. Okay, so get the roots of this will be t squared minus 4 plus 3 equals to 0. If I factor out 3 common, so you'll get t as 1 and t as 3. While if I equate this to 0, I get t as, this gives me t equals to 2, or to just draw the sign diagram. Now put them on number line, Here, just make sure you draw a, negator here, because the time can't be negative. So you go just beyond that. So t, this is velocity sign diagram, v of t, and I'm drawing his a of t here. So v of t, this is 1 here and this is 3 here. Now obviously you can put out one values in each interval, but if I know this is a happy phase graph, so the graph of this is something like this. So you can see clearly here it is negative, here it will be positive, and here it is positive. Or you could take a value, like for example, I take 4 and I plug in here. So 4 squared minus 16, that's your 16 minus 16, that's your 0, and plus 3. So it's coming positive. In between 1 and 3, you can take 2, let's say. If I take 2 here, so 4 minus 8, which is negative 4, and negative 4 plus 3 is coming negative. So obviously you plug in this expression because that's exact velocity. This is the simplified one. But if the value here is negative, automatically 3 times that will be also negative. So in this case, 0 to 1, let's say if I take the t as, let's say, half or something, or you can take, let's say, 0, and if I plug in 0 in this, it'll be positive 9. So it clearly indicates that this is positive, negative, and positive. So that's your sign diagram about the first one. Now, as far as the second sign diagram is concerned, where the acceleration is given, here it is 2. Now, before 2, if I plug in, let's say, 0, it will be negative here and it is positive here. So, according to the sign convention, like if you look at between 0 to 1, the particle is moving towards the right, and the acceleration of this is becoming negative. It means it is slowing down with the moving to the right. 1 to 3, between 1 to 3 seconds, it was moving to the left because velocity is negative. And then from 3 onwards, so at 3, so it's like this. So up from 0 time it started, it went to the right, it stopped at 1, and then it reversed the direction and started coming backwards towards 3 until time t equals to 3 seconds, and there it stopped, and again it took the direction change. So it's like from here it started, it went to the right, took the direction, changed back again, and it is like this. So here it is time t is 1, and here time t is 3. So one of the interesting questions that you'll notice is that find out the point where it changes the direction, where the particle changes the direction. So wherever you want to find out where the particle is changing the direction, so v of t must be 0. The velocity must be 0. So let's say now here, if I already have got t is 1 and 3, at which it is 0. So already we can say that at 1 and 3, the particle will change the direction. So that's the C part. Now describe the initial conditions and hence describe at this instance. So in initial condition is always by plugging t as 0. So first is initial s of 0 is at -1. V of 1 is, let's say, v of 0 is at 9, and a of 0 is basically, if I take, is -12. So acceleration is -12. The v of 0 is 9, and s of 0 is -1. So at time t equals to 0, the particle is at -1 position. So which means that it is 1 unit to the left of the origin. So this is the origin. It is -1 units from the origin left of the origin. This is where it starts the motion, and then it goes towards the right. So let us see the next part. The next part is find out the position when it changes the direction. So find out the position of the particle when it changes the direction. So S of 1 and S of 3 is something that we have to find, because we already found where it is changing the direction. So let's plug T as 1 here. So S of 1 and S of 1 and S of 3, if we can find out. So when you find out the position at s equals to 1, that's 3, and s equals to 3, that's -1. So basically what's happening is, if you look at this motion diagram, when you draw, this is called motion diagram. So when you draw a motion diagram is basically to show just like how is the particle like moving, in what direction it is moving and all. So this is the origin at time t equals to 0. It was at -1. Remember that on x axis is the position. There is no, this is not time. So at t equals to 0, it was at -1, and after 1 second it came to 3. 1 second here it was at 3 meters from the origin. So started its motion, moved basically 4 units to the right, and then went back again here after 3 seconds. So at 3 seconds, it went back here again. So because its initial position, I mean, S of 3 and S of 0 is the same. So it is at basically back to the same position. So yeah, so this is what it is. And then after this also direct changes the direction. So it doesn't go towards the right, it is changing the direction. So it is moving this way. So here the question is that draw this motion diagram. This is what you're going to draw. So you're going to just mark the position. So 3 units away from origin, and this is 1 unit away from origin. So total distance travel, if you see, is 4 units here and 4 units here in the first 3 seconds. So from 0 it starts, it goes 4 units to the right, and then once again it travels 4 units to the left. So that's what is the net distance travel is going to be 8, and net displacement will be 0. So that's how you tackle some of the basic key terminologies of the kinematics topic. So here the expression has been given for displacement, which is t cubed minus t squared minus 5. Of course, t is greater than or equals to 0. And what we are supposed to find out is the v of t, a of t, and their sign diagrams. So firstly, v of t here is going to be the derivative of the displacement, which is 3t squared minus 2t minus 5. Derivative will be 0. So it'll be 3t squared minus 2t. That's the derivative of this. Next up is the acceleration expression, which will be 6t minus 2. Now, next part is to draw the sign diagram. So if I draw the sign diagram for both of them, just put this stopper, and the first thing you'll draw is the velocity one, v of t, then you have a of t. So v of t sign diagram will be basically only at one point, because if I factor this out, it'll be t and 3t minus 2 will be 0. So t is 2/3. So you're going to get t as 2/3 here. And in this case, here it'll be t equals to 1/3. This will be 1/3. So now our next step is to actually put the sign values. Like if I plug in, let's say 0 here in the first expression, I mean, not 0, if you take a value, for example, maybe 1 in this side. If I take 1 here, it'll be 3 minus 2, it's positive. So it'll be positive here. And of course, this will be negative because this is a root, so it'll be negative. And between 0 and 2/3, if you plug, let's say 1/3 here or something, you'll get negative value. Similarly, if I have this acceleration one here, 6, this will be negative, and here will be positive. So coming to the next one is like, okay, so interpretation of this is that between 0 and 2/3 time, the particle is moving to the left between 0 to 2/3, and beyond after 2/3, it is moving to the right. At between 0 to 1/3, particles velocity was decreasing, particles velocity is increasing. So after 1/3, so if when you look at the acceleration sign diagram, if acceleration is positive, velocity is increasing. If acceleration is negative, velocity is decreasing. But we can't say speed increases or decreases according to acceleration sign diagram. I'll come to that because that's our last point here. Now let's talk about the initial condition. Now, second is find where particle reverses direction. So it'll be where v of t is 0. If I say the b part, v of t is 0, obviously at t is 0 and t is 2/3. Since at t equals to 0, the motion starts, we'll take consideration of t being 2/3 as the position. Next one is the finding out the motion diagram. So for motion diagram, we always need to have the initial position. Initial position will be s of 0, which is -5. Then v of 0, which is going to be 0. V of 0, you can see 0. Then a of 0 is at -2. So these are the three values. Now D part, for D part, we find out first the position where it reverses the direction. So S of 1/3, let's find out. Let S of 2/3 when we find out. It'll be 2/3 cube minus 2/3 squared minus 5. So it'll be 8 upon 27 minus 4 upon 9 minus 5. So if I simplify this, what I get is, so Finally, when you draw the motion diagram, in motion diagram, what we do is we find out this is the origin. At time t equals to 0, the particle is at -5, means 5 units away from the origin. So it starts the motion from here actually. So the motion is starting from here. Then you can see that after 1/3 second, after 2/3 second, where it reverses the direction, t equals to 2/3, it has reached to -5.148, and from here it reverses the direction. So this is the motion diagram that we were looking forward to. And now coming back to the final part, where find where speed of the particle is increasing or decreasing. Now for this, I would put a very simple context is that if you look at some parts, like where you can see that velocity sign diagram. Now, if I look at the velocity graph, we suppose, let's say this is like the velocity graph. Now, velocity negative being doesn't mean that magnitude of velocity is lesser or it is reducing. Velocity, when I draw the absolute value of this velocity, I get the speed function. If I draw the speed function, it'll be something like this. So this is the speed function actually. If you draw the absolute value of velocity function, you get the speed function. Now, number one here is that if you look at the velocity actually was decreasing, velocity was decreasing here because the slope was negative. But in the same interval, speed is increasing because you're referring the speed as a magnitude at which you're traveling. And velocity also takes account of direction because it is becoming more and more negative in that time interval because you're moving away from the origin towards the left side. So what happened is that when you talk about the velocity being negative, it simply means that it doesn't mean that speed is also decreasing. So in that case, you need to use the culminated sign diagrams that you have drawn. Okay. So in the interval with the observations that we have is in the intervals where both the sign diagrams of v of t and a of t are either positive or negative. Their speed will be increasing. And in the intervals where the signs are opposite, like for example, if velocity is positive, acceleration is negative, or velocity is negative and acceleration is positive, then in that interval your speed will be decreasing. So let us just see that here. When you look at this sign diagram, if I project the critical times here, so there are three time intervals: more than 2/3, between 1/3 to 2/3, and between 0 to 1/3. Now, between 0 to 1/3, if you see, the both the sign diagrams are the same. So in between 0 to 2/3, between 0 to 1/3, speed is increasing. Firstly, between 0 to 1/3. Now, from between 1/3 to 2/3, you can notice that this is positive here because this sign diagram is positive from 1/3 onwards. This is positive and this is negative. So if one is positive, other is negative, you will notice that the speed is decreasing in that case. So third case will be where both are positive. So in this case, you can see that beyond 2/3, it is positive. So again, if I take t more than 2/3, the speed again increases because the signs are the same. So just to check on if the speed is increasing, you don't look at the acceleration sign diagram. If they ask you velocity is increasing, you just look at the sign diagram of acceleration. Acceleration sign diagram positive is velocity is increasing. Acceleration sign diagram negative, velocity is decreasing. But for speed, you need to take care of both acceleration as well as velocity sign diagram. So if acceleration and velocity sign diagrams both are positive and both are negative, in that case, you will have speed increasing. In case where acceleration is negative and velocity is positive and vice versa, in that case, speed will be decreasing. Let's take a evidence also, like on technology, that how is this all happening.